Mantovani.
All right, thanks for the introduction, Catherine. Good afternoon to everyone. Today I'm going to show you some results that I've been working during this period as a DTC visitor. So the presentation is about test and evaluation of the MPAS model in the reproduction of mesoscale convective systems over mid-latitude and tropical regions. The background and motivation of this project is because mesoscale convective systems often occur over mid-latitude and tropical regions, and they are responsible to produce severe weather and cause profound impacts for society. So here you have a picture of a figure from the work of Cuiral 2026, showing the relationship of MCS and the production of severe weather in the US. So definitely for some severe weather events, we have a more impact of MCSs. But specifically in some regions, for instance, the Southeast, we have occurrence of tornadoes with more intensity and also more frequency related to MCSs. And a recent NOAA report indicates that severe storms accounted for 50.8% of billion-dollar weather disasters. And as we can see here in this picture, the green bars are the severe storms. They increase year after year. And this impacts the region of central US and southeast US. In terms of numerical modeling, even state-of-the-art numerical weather prediction models, they struggle to accurately depict the precipitation and low-level conditions associated with these systems. But not only numerical weather prediction models, but also climate modeling reported some persistent biases related to the misrepresentation of MCSs. So accurate representation of MCSs is essential for improving forecasts. And also part of the motivation of this project is because this is within a broader effort towards advancing community adoption of MPAS through testing and evaluation. So some objectives are test and evaluation of MPAS to reproduce mid-latitude and also tropical MCSs and associated severe weather. Identify the model ability to reproduce MCS features, and evaluating the simulated precipitation and surface conditions associated with the MCS passage. And some scientific questions are, for MCS severe weather prediction, does the global 63 kilometer variable resolution MPAS outperform the regional 3 kilometer MPAS? Because this is the main feature of MPAS, the capability of produce variable resolution simulations. And so this comparison against this traditional limited area model approach is a good way to see if the model is doing better. So which physics suites produce the most skillful precipitation forecast for MCS events? And also if MPAS can reproduce tornado favorable environmental signatures consistent with the observed outbreaks. We don't have the fourth question here, but I would like to see if the same skill for mid-latitude MCSs we can get when we are looking at the tropical systems. So to do that, we selected 4 cases. The first one is the southeastern case in the US, which took place between March 3rd to 31st. Here we have a summary of the atmospheric conditions at 18 UTC on March 3rd. So at the upper level, we had like a robust jet stream and a negatively tilted shortwave trough, northeastern Texas. And this promoted the upper level divergence and large scale ascent to promote the storms in this event. And when we look at the reflectivity fields from MRMS, at this time we have a strong squall line that moved eastward. And at the surface, we had a 992 millibar mid-latitude cyclone over Wisconsin that also promoted the fuel for the storm's formation, and a cold front pushing through the southeast. And on top of that, we had warm, moist air coming from the Gulf of Mexico. This provided the right conditions to the occurrence of severe weather, basically high shear and low cape. And this case is a very good case to show us the impact of a single storm. So between 12 UTC on March 30 to 12 UTC on March 31st, we have here the MRMS reflectivity at 3 times, overlaid by SPC reports. We can see how impactful a single storm could be because it generated basically 114 tornadoes, ranging from enhanced Fujita scale 0 to 3. And the single storm corresponds to 38% of occurrence of March 2022 tornadoes. Also, we had like more than 300 wind reports, 2 large hail, 2 deaths, 17 years, more than 200,000 power outage. And this single storm produced $1.3 billion in economic losses. So this is just to show us how important it is to better understanding and modeling those systems. All right, in terms of the performance simulations, we tried to explore all the possible aspects. So we started to testing some different initialization lead times that are basically these times here. We tested both modeling frameworks, and we tested the available physics suite to see the sensitivity of the physics. So in terms of the model configuration, here I'm showing in this right figure the innermost high resolution region of the 63 kilometer mesh. And this black dashed box represents the regional 3 kilometer domain that was cut out from a quasi-normal uniform 3 kilometer global mesh to ensure that all grid cells have a 3 kilometer resolution. And basically, for this case, I tried to ensure that we have the same amount of mesh size, or at least the same, to ensure a fair comparison in terms of computational resources. So here we have the other model configurations, like 65 model levels, 31 kilometers was set up the model top. In case of the regional run, we turn it off convection. And for initial condition, and in case of the regional runs, the lateral boundary conditions were provided from the CMWF IFS. Regarding the physics suite sensitive, we tried both convection permitting and mesoscale reference that are the physics suite by default available in the MPAS. But also we tried the NOAA GSL or HER v5. And in case of these simulations, it's from the MPAS is from a different repository. It's from the UFS repository. And by the way, this version is particularly from early February this year. So in terms of the parameterizations, we have some difference among them. So the results should be interpreted as a joint contribution because we have differences in terms of convection, microphysics, PBL, surface layer, and also gravity wave drag biography. And another commentary here is that the NOAA GSL physics suite was developed to work with priorly HER initial conditions and lateral boundary conditions, and they originally makes use of Rook LSM, but here, because we are using the IFS, we need to change to NOAA LSM. All right, so in terms of data and evaluation strategy, the model evaluation is performed during the period where we had the event, this tornado outbreak between 12 UTC on March 3rd to 12 UTC on March 31st. We used all this data like Radisson soundings from University of Wyoming database, surface observations from sign-up in METAR, GPM merge brightness temperature, grid depth precipitation from stage 4, and reflectivity data from MRMS. So MPAS outputs were basically regridded to a common regular latitude longitude grid before comparison using Convert MPAS tool. And to ensure the same resolution, we choose the 4 kilometer resolution to match brightness and precipitation resolutions. And also we interpolated also the MRMS to the same resolution. So here we are looking at the results at 4 kilometer resolution. Basically, to conduct evaluation, used the traditional metrics performed to perform the evaluation, like bias, root mean square error, correlation coefficient, fraction skew score, performance diagram, and dichotomous metrics. Well, in terms of the MCS tracking, as we are interested in better understand how well the model can reproduce the systems, they were tracked using the PyFlex tracker MCS algorithm, following the MCS MIP protocol, that basically are these criteria definitions. And the simulated outgoing long-wave radiation on the top of the atmosphere is converted to brightness temperature using an empirical relationship following Youngian's lingo, because MPAS don't have these brightness temperatures as a default output. And basically, the MCS tracking is conducted considering both observed and simulated data sets. And finally, the tornado proxy analysis. 3-kilometer MPAS cannot explicitly reproduce tornadoes, but you can check some storm parameters. All right, so starting with some results, here we have the initialization lead time experiments, starting at 12 UTC on March 29, starting at 0 UTC on March 3rd, and starting at 12 UTC on March 3rd. As you can see here, the storm is very impacted by the initialization lead time. As we can see, as we get closer to the mature stage, that is indicated by this vertical red line here. So we are probing at this time 0 UTC on March 31st. As closer we get from this time, the brightness temperature fields get better. And this is expected because storms are very sensitive to the initial condition. And in terms of precipitation, here in the bottom row, we have the precipitation this time. This mask behind the precipitation contour is basically the brightness temperature field showed in the first row. So in general, model was able to reproduce the storm independently of the initialization lead time, but the earlier initializations were able to better reproduce the convective initiation and in general, the whole MCS life cycle. So we have some difference too in terms of MCS propagation and speed. As we can see here, the closer initialization have a better agreement in terms of these MCS features. But we decided to use this initialization at 0 UTC on March 3rd because it reasonably reproduces the MCS life cycle and ensures a 12-hour spin-up period. All right, so regarding the modeling framework experiments comparing both the global and the regional approach, we have a larger difference here. For instance, the regional run kind of shifted the peak of volume of rain, and also we have larger differences in terms of storm propagation. And as we can see here, we also have huge differences in terms of storm structure during the well-developed stage. That is basically related to the large-scale forcing and the influence of lateral boundary conditions. Another interesting difference that I found is that the global runs could better reproduce the amount of rain, for instance, in a cross-section at 33 degrees latitude north, that is somewhere here. As we can see, the regional run is producing like these spurious, more intense precipitation reaching almost 80 millimeters per hour that is not observed in the stage 4. And when we look at the total hydrometeor loading and the microphysical reading heights, we can understand that the global run is better reproducing the storm structure, as you can see here in comparison to the regional run. So basically, this difference comes from the lateral boundary conditions and also the size of the domain. Since the last week that I presented the half-hour seminar, I could run another simulation with a larger domain that improved the storm structure. I'm not showing the results here, but basically we have the impact of both the size, the domain size, and also the lateral boundary conditions. So that's why the global run is slightly better. And it translates in the better skew in terms of precipitation verification. Here we are validating the forecast hours between 12 to 36 hours. And as we can see, the global run is skillful when compared against the regional run. And also it has a better performance. In terms of accumulated precipitation for this period, both were able to reproduce the observed accumulated precipitation from stage 4, but the global run was slightly better. So in terms of surface verification against SINOP and META observations, we can see some difference. For instance, the regional run showed like a warmer bias, and the global run a colder bias. And this warmer bias from the regional run comes from the influence of lateral boundary conditions. And also the more prominent difference here are in terms of surface pressure. As you can see here, the regional run has a huge bias and is very different than the global one. And it basically tells us that this difference comes from differences in surface, storm propagation. And it translates in this difference that we can see in the surface pressure. All right, so regarding the tornado proxy analysis, basically computed the SIGTOR significant tornado parameter following Thompson. That is this equation here. And as we can see, both both simulations are useful to indicate the occurrence of tornado in this region. Here we can see the SIG tornado parameter for the period and overlaid by SPC reports. But the regional run showed a better true skew score for this case because we had like more CAPE from this run. Here we have the difference between global and regional that indicates that the regional run had more CAPE, and that's why we are seeing here more intense SIG tornado parameter values. But in general, both runs were able to indicate the probability of occurrence of these tornadoes. All right, so moving to the physics suite experiments, here I think we have the biggest difference. As we can see, for instance, in terms of CCS area, we have a big difference between them, with the convection permitting physics suite getting closer to the observed peak during the mature stage. And also we have difference in terms of volume of rain. So the NOAA-GSL scheme had less precipitation, but in general, the MR physics suite had a better agreement during the whole MCS life cycle, particularly to reproduce the convective initiation that is very difficult. And also both CP and MR had a better agreement in terms of MCS propagation. Well, the difference are not too much in terms of the storm structure at this time during the well-developed stage. Both CP and MR showed a more closer pattern in terms of brightness and temperature. And I would say that CP is slightly better at this time than the other two. So also it translates in difference in precipitation verification, as we can see here. In general, all these three simulations were able to reproduce the observed precipitation seen observed in the stage 4 data. But the CP and MR were slightly better in terms of skew. It's skillful than the NOAA-GSL, especially for more intense precipitation thresholds. The dichotomous metric basically indicates to us that the MR is slightly better than the CP, and the model is suffering the double penalty problem as we are like evaluating at 4 kilometer horizontal resolution. And the performance diagram basically tells the same, as we have CP and MR slightly better than NOAA-GSL. So in terms of surface verification, one more time, we can see that we have a larger difference in terms of surface pressure because they are kind of propagating the storms with differences. So as you can see here, the MR had a better agreement with near zero bias. So MR is doing a really good job in terms of surface or in terms of storm propagation. And also we had like less biases in terms of temperature and wind. So regarding the pre-MCS environment for these runs, this is a probe in Jackson, Mississippi. In general, model shows a good agreement for the vertical structure. We had more difference in the 700 hectopascal layer from the NOAA-GSL. Also, the MR for this probe has more CAPE and more intense, for instance, supercell composites, and also significant tornado parameter. But in general, the NOAA-GSL had more intense significant tornado parameters in general over this area due to, in general, more intense conditions and CAPE, particularly for this case. And it gives us through a more skillful simulation for this parameter. All right, so moving to another case, the second case is also considered a mid-latitude case, but in astrotropics, that is the Southern Brazil case that took place between 7 and 8 November in 2025. In this case, we had this is a really good footage of a supercell storm. We can see the rotating storm pretty clear here. In this situation, we had like a warm, moist air coming from the Amazon, transported by the South American low-level jet. And also we had a strong cold front driven by an extratropical cyclone that was configured here in this part. Sorry, but this synoptic figure is not properly showing this. But we can see, for instance, the right conditions to the storm's formation, as you can see, intense values of omega at 500 hectopascal layer. And this promoted the formation of squall line, and the low-level jet triggered this supercell that we can see here, and also tornadoes. So the severe weather reports for this case is basically preliminary. We had almost 19 tornadoes ranging from EF0 to EF4. We had like 5 deaths, more than 800 injuries, and a small town was almost destroyed. Oh, what's going on? The screen is frozen there. Yep. Yeah. So, and we had like $22 million in economic losses. So the question here is the 63 kilometer simulation performed better for the US case. But the question is, does that hold for a different event in a different environment, but still a similar storm? So basically, for this case, we just tried the NOAA-GSL physics suite. The approach is pretty the same. We just tried to make sure that the regional domain has the same amount of mesh size to ensure a fair comparison in terms of computational resource. And the data and evaluation strategy, again, is the same. Basically, what changes is the period. And because we don't have stage 4 there, we used the emerged precipitation. One commentary here is that this is not the final run, this is the late run. And as we emerging has 10 kilometer horizontal resolution, we regraded all the MPAS outputs to 10 kilometer and also merged brightness and temperature to ensure the same resolution in the comparison. So here we have some results for this case. In general, both runs were able to reproduce the MCS life cycle, as we can see here in the MCS features. We have a more prominent difference from the regional run. As you can see here, we had a more intense CCS area that translates in more intense volume of rain and also more intense propagation distance and speed of this storm. And when we look at the snapshots at 22 UTC on November 7, we can see some interesting difference as the regional run is producing like a spurious brightness temperature that is not observed in the merged brightness temperatures, but also precipitation in this part of the domain. And in this case, the global run matches better with what was observed. And in terms of pre-MCS condition, I think both runs were able to reproduce the vertical structure of this sounding. This sounding location is exactly here. This is Foz do Iguaçu, is a city in the Paraná in Brazil. Unfortunately, we don't have like a sounding closer to the passage of the system. This should be 18 UTC, but it's 12. But in general, it shows us that the model is doing a good job in terms of the reproduction of the vertical structure. Well, the precipitation verification for this case, in terms of skill, both are very similar. The more permanent differences are in the most intense thresholds for precipitation. And also, I'm highlighting here PR. PR is basically the Paraná state in Brazil, that we have more differences as the both underestimated the precipitation observed over there. But this first hours of the storm, as the storm propagated from south to north, we had a good agreement in these regions here. In terms of surface verification, one more time, we have the global run doing a better storm propagation, as you can see, a near zero bias for surface pressure, but also a better comparison with the 2-meter temperature. That indicates to us that the model is doing a better work in terms of the cold pool propagation and reproduction. Well, in terms of the tornado proxy analysis, the global run had a better skew. As you can see here, the regional run was not able to indicate the more intense and, by the way, SIG tornado 1 in the region that we had the occurrence of tornadoes during this case. And that's why the skew from the regional run is lower in comparison to the global run in red. And one more time, this comes from some differences in the storm parameters as CAPE, storm relative helicity, and shear. As you can see, we don't have too much differences in terms of CAPE, but the global run had more storm relative helicity and also shear. And basically, my guess is that the regional run is being impacted by the lateral boundary conditions in this case, and possibly is not properly reproducing the low-level jet during this case. So this is basically a summary of some results that I worked from Amazon MCS. And the question here is, as you could see, MPAS is doing a good job in reproducing MCS, especially the MCS features. But basically, this is a summary showing how difficult it is to reproduce tropical MCSs. So these runs were made using ERA 5. It's a little bit different than before. It's a case on 12 April 2015. We used the Global 623 mesh. That is basically the same approach as before, but the innermost high resolution region is centered over central Amazon. And we can see here some snapshots on 12 UTC on April 12. So the model is showing really different brightness temperatures structures. Here we tested not only the ERA 5, but also GFS, sorry. And we tested the convection permitting physics suite and the MR. And also we changed the convection parameterization from the convection permitting physics suite from Grau Freitas to the new TTC. But basically, as you can see here, is very difficult to reproduce the MCS features in these Amazon cases. And particularly, this convection permitting physics suite is producing spurious convection. And my guess is that the Thomson microphysics could be generating this spurious convection. Because if you look at time, hour by hour, you will see convection being produced everywhere. That is not the true in the MR. So possibly the WSM6 is doing better for this environment. And this translates in lower performance and skew in terms of precipitation, and also is very difficult to reproduce the cold pool characteristics. This convection permitting physics suite with the switched convection for new TTK better reproduced the cold pool at this time, but with some still negative bias. And in terms of precipitation, as we can see here, is way different from the previous cases, mid-latitude cases, when we have the models like underestimating the observed precipitation. So this is another case. Sorry, I ended up not mentioning the previous case was during the wet season in the Amazon. That is supposed to be more difficult to reproduce. And this is a dry case during the dry season, but it's still very difficult to reproduce the MCS features. It's slightly better than before, but yeah, it's very different from the mid-latitude cases. This MR run with the ERA 5 is slightly better than the CP. And one more time, as I said, CP is like producing too much convection, spurious convection, probably related to microphysics. In terms of precipitation verification, is slightly better than the wet case, but in terms of cold pool characteristics, it's very different because we have some spatial and temporal displacements when compared against the observations. So some concluding remarks are the MPAS demonstrated skill in reproducing two high-impact quasi-linear convective systems over mid-latitude regions with embedded supercells in both North Hemisphere and Southern Hemisphere. The global 6 to 3 kilometer simulation outperformed regional 3 kilometer in both cases with better MCS features. As expected, shorter lead times improved MCS structure and precipitation in the global framework. CP and MR physics suite showed better precipitation skill than the NoJSL-led physics suite, and MR better captured convective initiation time. Convective initiation and dissipation remain the most challenging life cycle stages, regardless of configuration. And the Brazilian case, the case 2, basically revealed additional limitations from the regional framework regarding the SIG tornado parameter that is probably likely tied to cold start spin-up or boundary layer overmixing. And the Amazon MCS cases highlighted the difficulties in reproducing tropical MCSs. And I'd say that the best approach to conduct analysis using Amazon MCS cases like conducting a long-term simulation and evaluating the model statistically. So some next steps in future studies would be extending these analysis to other high-impact severe weather cases to assess configuration robustness. And we have some issues with the Southern Brazil case data. That basically data is preliminary, and we are working with folks over there to get this data. And also, I would like to see the impact of data simulation within the MPAS JEDI in terms of improvement of convection initiation timing and cold start spin-up, because I had the opportunity to join the spring forecast experiment last April. And I saw some really good results of MPAS JEDI in terms of this convective initiation timing. And probably these results can be impacted by this approach. That's it. Thank you very much.
Is this working? Okay. All right. So we can take questions from Mantovani, both from in the room and online. I'll try to rotate between if there's questions in both places. So if you could raise your hand online and then we can get to you. But are there any in the room to start?
Great talk. I noticed that your regional version and the global 6 to 3 kilometer version has one obvious difference is the convection or cumulus parameterization.
Yeah.
Do you think the full performance of the first case would tie to this? Because you mentioned other things, but you never talk about whether the shutting off the cumulus scheme in the regional run is actually one of the main reasons.
Yeah, good question. So let me go back there. So these updated Mallory Yamada Nakanishi with the edge diffusivity mass flux have this shallow convection built inside. So I would say that even when we turn it off convection for the regional case, we have the contribution of shallow convection in this run. But definitely it's not an easy task to say from where comes this difference, because we have huge difference. We don't have like well-controlled experiments, but definitely could be impacted by these differences. Yeah, we can make better controlled experiments, but I think we would like to see the physics suite as they are provided to the MPAS user, basically.
All right, I see Chris Castro has a hand up. Chris, do you want to unmute and ask a question?
Yeah, very nice talk. Sorry, I'm not there in person. I needed to eat my lunch after the last seminar. But my question and comment is, have you thought about, for any and all of these runs, doing an ensemble-based approach? So instead of like your lines and your forecast traces, like they're clouds, and you can characterize the uncertainty. And I'm saying that because if you do want to do the data assimilation step, whether it's something like an OSE or an OSSE type experiment, you're going to need to do the ensembles anyway.
Yeah, I think definitely the ensemble should be the best approach as possible, but it requires more computational resource and efforts. But yeah, I think the ensemble should be a good move for next studies.
Other questions?
All right, thanks. All right.
Yeah. If you do have a question, if you want to
Yeah.
come off mute, because it's hard to read in the room.
Yeah, but I saw the Shizangi question.
Okay.
Thanks for the questions. So I think the regional run was slightly worse than the global, because, as I said, these two things. The first one is the size of the regional domain that was constrained by the mesh size to ensure more a fair comparison in terms of computational resource. I did the seminar last week, the MCube Happy Hour seminar, and the question was the same. So I tried to run the model again using a larger domain, a Conus 3-kilometer domain, and definitely it improved the storm structure. Not too much in terms of MCS features. I also need to look at the precipitation results. But I would say that two things: this domain is being impacted by the, bottom lateral boundary that is closer to the study area, and in general due to the LBC. But when I said that the the global was better, is in terms of precipitation and surface verification results, basically, and also in terms of storm structure. There is another question.
Yeah, it looks like Jia has hand up. So if you want to speak to the question, Jia.
Hi, can you hear me?
Yes.
Great, thank you. Nice presentation. I have maybe two questions. One is, I guess you maybe it's the previous slide, you talked about one of the physics suites performs better than the others. Since I'm not familiar with MPAS, I'm curious, are these different suites designed for different purpose? Like one is more for like short-term weather forecasting, like what you're doing here, versus like a longer-term climate simulation? That's my first question. Maybe you can answer this first. Hopefully it's easier, and then I have a follow-up on that.
Yeah, definitely. They are very different, as you can see here. And yeah, in the very first beginning, our task was just to test what we have available in the MPAS. Hopefully in the future, more physical parameterizations will be implemented into MPAS, so we can mix them and make more tests. But Yeah, I would say that convection permitting physics suite is doing a really good job in some cases, but MR is doing also a good job in some cases. And I would say that the Node.js had a lower performance because we are not using it as it's meant to be used, like with the Rook LSM and, you with her initial conditions and lateral boundary conditions. So yeah, there are some difference. Yeah.
Okay.
Mhm.
Thanks. Yeah. So I guess my follow-up question is, if I remember right, you said one of the maybe like the MR suite for the US case seemed to perform better, and you show a suite of different metrics. I was curious, did you look at something like a finer scale? Like this is like a really big scale. Right? You track the MCS as you look at the overall storm structure and rainfall volume. But I was curious if you looked at like finer scale convective structures, like what does the updraft look like, the sizes, the intensity, how they're related to the precipitation produced in them, whether there's like a significant difference between the physics suites, and then how does that compare to like observations where, for example, you have in the US you have MRMS, and so things like the convective cell sizes, their associated rainfall, convective stratiform precipitation separations, which the kilometer scale models tend to always have a struggle. So I'm curious whether the different physics suites, one might perform better than the others, and why. And so that could be quite informative in terms of understanding their bad and good and bad, I guess.
Yeah, thanks for these questions. And yeah, definitely, I would take this as a suggestion. We had no time yet to do this kind of analysis, but I will keep working with these results for the next upcoming months, I think. And I will do that. Actually, I did when comparing regional and global runs like this. I think it's kind of what you said in terms of separate the grid scales. But yeah, definitely it's a good approach to better understand the difference among them.
Yeah, I mean, having up some observational target would be useful here, right? The leveraging something like MRMS, where you have really fine scale structures. Like within this score line, I imagine there's a lot of embedded cells and their sizes and depths and things like that that are pretty sensitive to different physics parameterizations, and that would be your observed targets, and then particularly associated with their rainfall productions. And these things are observable, whereas something like heating, we can't really directly observe that, right? But that will be complementary to what you're doing here.
Yeah, sure. Yeah, I look at that, the reflectivity fields from the MRMS. I ended up not showing these results here, but the CP and MR are producing a more intense reflectivity fields in comparison to the Node.js that at this aspect is better.
Mm-hmm.
But definitely I should look at the precipitation from this data set to, improve the analysis. We have another question there.
Yes, the other Joe wants to.
Yeah.
You want to read it?
Yeah, thanks for the question. Yeah, definitely. I think if we conduct a fine tuning with the physics parameterizations for that environment, we could definitely get better results. I recently published a paper in the Weather and Climate Extremes evaluating MPAS against an operational WRF version for southern Brazil. And yeah, as we know, we have a case-to-case variability, and for some cases, the CP are better than MR. So we need to test. There's no other way to find out, but definitely if we do some fine-tuning, we can get the results better for these different environments. Yep.
Other questions in the room? Oh, here. Let's see if I can throw this thing back.
This is very
There. Really nice talk.
Oh, thank you.
Enjoyed that a lot.
My question is about the tropical precipitation being underestimated in basically all the cases. So you mentioned microphysics being one explanation. Do you think there's anything else going on, like, PBL scheme, or have you tested some of those differences? Because I think a lot of people are seeing underestimation in tropical areas.
Yeah. So, and I think the persistent biases from climate modeling comes from these difficult to reproduce MCSs over there. So as we know, is like a weakly forced environment. It's not good as the same as here in Southeast, like we have a very pronounced large scale forcing. So the difficulties start there. And also in Amazon, we don't have like a very specific triggering for convection. So this is make even difficult to reproduce. But I had a good meeting with Song Yu Han yesterday, and he said that possibly the spurious convection that I'm seeing from this convection permitting runs, I mean, using the convection permitting physics suite, could be from the Thomson microphysics. And he said to me that possibly the WSM6 is better, and definitely I think is better because when we look hour by hour, these snapshots from the MR physics suite experiments, we don't see this spurious convection. Unfortunately, I ended up not showing these results, but I can show you later if you want. We have like spurious convection being produced everywhere inside the domain. So I don't think we have this in nature.
Thank you.
Yeah.
This my comment was suggest more than a question. Coming back to your very first experiment, I would like to echo Zhe Zhang's comment in terms of the hypothesis. One, when you test this two different version of either global 6-3 or 3 individual, that of course they have their own purpose of configuring up this way. But the advantage of MPAS, in our opinion, one is the global representation, the other is the variable resolution, right? The gradual change of the grid sizes. Maybe the more, in my opinion, a better comparison or experiment is to actually cut out, if you go back to your grid setup, cut out the regional one as the global one with a little bit of the 60 varying to 3 as a regional setup, and then compare that with this global to really see the advantage, whether it's coming from the global representation or just because the changing the resolution variability. So I would see that as a more, I would say, a valuable test rather than the direct comparison of a pure 3 resolution compared to a varying resolution simulation.
All right, thanks. Yeah, if I'm not mistaken, I mentioned it. I made another simulation, use a larger domain, a Conus 3-kilometer domain. Yeah, but it's different. But yeah, it's a good suggestion. Thank you.
Any other questions for Mantovani? All right, if not, let's go ahead and thank Mantovani again for the great presentation.